Hi guys, today we'll take a look at the topic of momentum. So momentum has a very straightforward definition, but it has some pretty interesting consequences. So we represent momentum with the symbol P, and it's defined as the mass times the velocity vector of a particle. So if I had a particle mass m and it's moving with some velocity v in that direction, then the momentum is simply the scaled vector of velocity, right? Because if you're multiplying by a scalar m, all that does is it changes the length of the vector, but it keeps it pointing in the same direction. So let's say I scale it out by this much, so I have a momentum vector pointing in the same direction as the velocity vector. Now the units of momentum, units of mass is kilograms, and unit of velocity is meters per second. Therefore the units of momentum is kilograms meters per second, or you can show that this is also equivalent to Newton seconds. So this is it. This is the definition of momentum. Momentum is simply mass times velocity. Now, where momentum gets interesting is where we take a look at Newton's second law. Now, we've learned earlier that Newton's second law, we were told, is that the force is proportional to the acceleration, where the constant of proportionality is the mass. Now this is not quite right, because when Newton defined force, he defined it in terms of momentum. And here's what Newton basically said. He said that the net force on an object, right? Net force being the force, the resultant force you get after you vector sum all of the forces on the object. This is equal, excuse me, it's equal to the rate of change of momentum. Now don't worry if you're not familiar with the differential notation here. I can also write this as net force being just the change in momentum over the time over which that change happened. Now this is the real Newton's second law, not F equals ma. And I'll show you in a minute why this is. So let's take a really simple example. So let's say I have a wall and I have a piece of plasticine here, right? A piece of plastic here, and I just throw it against the wall with a speed of 5 meters a second, and the mass of this piece of plasticine is, let's say, 200 grams. And then when it hits the wall, it comes to a dead stop. So it's not moving anymore once it hits the wall, right? So whenever you take the change in something, what you do is you basically just take the final value of the thing and you subtract the initial value. That's what changes, right? So for example, if your temperature goes from 20 degrees Celsius to 50 degrees Celsius, the change is 50 degrees minus 20 degrees, which gives you 30 degrees. So momentum we saw here was mass times velocity, so I just simply plug that in. Mass times the final velocity, and then mass times the initial velocity, right? And the mass I can factor out, so I'm just looking for the change in velocity. Now since it came to a dead stop, that would be the final velocity, and this would be the initial velocity. So it came to a dead stop, which means 0, and the initial velocity was 5, and the mass is, converting grams to kilograms, I have 0.2 kilograms. So I simply get a value of -1 Newton seconds. Okay, so that's what the change in momentum is. I can go ahead and compute the force here. Alright, so the force is going to be equal to the change in momentum, -1 Newton seconds, and let's say that the time in which it took for this plasticine to kind of stick to the wall was, let's say, about half a second. So I divide that by half a second, I'm going to get -2 newtons. So what's the significance of this minus sign here? Well, I'd assumed that directions to the right was positive, hence why I wrote +5 here for the velocity. So a minus sign must mean that the force is acting towards the left, and that's what we would expect. So as the plasticine kind of gets stuck to the wall, there's going to be a force from the wall pushing on the plasticine. So the plasticine is going to experience some force from the wall pushing on it as it splatters against the wall. And so that's a simple example as to how you use the second law to compute force on an object.